For our final project, we decided to model and analyze different geometries of trailer hitch ball mounts and improve the design of the hitch with the most stress. Trailer hitch ball mounts are for connecting a trailer, boat, or whatever you need to attach to your vehicle. As shown in the picture on the left, the vehicle must have a receiving tube mounted on it so the trailer hitch can slide into the tube and be pinned in place. The trailer also has a receiving end that locks onto the ball mount. The hitch dimensions are determined from the rise, drop, hole size, and length shown in the picture on the right. Different geometries are needed for different fittings on different vehicles. We are analyzing the trailer hitch ball mount to determine where the maximum stress, strain, and deformation occur. This analysis is important because if the trailer hitch fails, then there could possibly be life-threatening consequences and large expenses involved. The three types of ball mounts we decided to analyze are based off of the CURT Class 2 ball mounts. The designs consist of an angled drop, and straight rise. Here are our 3D models designed in SolidWorks. The angled drop has a drop of 2 inches, the straight drop has a drop of 4.5 inches, and the straight rise has a rise of 3 5/8 inch. The boundary conditions we used on each of our designs is fixing the pin that goes through the receiving tube and the hitch. We made the vertical displacement of the bottom face 0 to simulate it resting on the receiving tube. The loadings we applied to each design are a vertical load of 350 pounds on top of the ball and 2,100 pounds on the ball pulling away from the hitch. 350 pounds is recommended by CURT Ball Mounting Company as the allowable weight that can rest on the ball. The 2,100 pound horizontal force represents the static friction of the tires on the road, which we took as 0.7, multiplied by the maximum allowable towing weight, which was 3,000 pounds, also recommended by CURT. This is the total force needed to initially move the trailer, which we are calling an overcoming friction analysis.
We meshed our design first using 0.1 inch quadrilateral elements to ensure accurate results, but then changed the mesh to 0.3 inches to speed up computational time and still end with similar results. The first analysis is of the angled drop that is just statically loaded. The max stress occurred where we expected, which is at the fillets of the welded parts of the hitch and the max deformation at the end of the ball. The tensile strength of steel is 80,000 psi, so this von Mises stress is well under the maximum limit before failing. The next analysis is of the angled drop with overcoming friction analysis, which shows a higher von Mises stress, which is at the neck of the ball, and there is still a high stress at the weld fillets. The straight drop statically loaded analysis shows lower von Mises stress, lower strain, and same maximum location, and higher deformation caused by a higher torque from the increased drop. The straight drop for overcoming friction shows slightly lower von Mises stress, strain, and total deformation. The straight rise statically loaded design has a higher von Mises stress at the bend radius, higher strain, and higher deformation. The straight rise overcoming friction analysis shows a very high von Mises stress, a high strain, and deformation. The von Mises stress is much greater than the tensile strength of steel of 80,000 psi. We believe this high stress is due to our model not being exact to the dimensions of CURT Mounting Company. This table shows a summary of our statically loaded and overcoming friction results. We recommend from our design to use a straight drop if the mounting geometry is appropriate. To improve the straight rise model, we enhanced our design by adding a cross-member support bar and also thickened the ball neck. For the statically loaded modified straight rise, the von Mises stress decreased by 45.8%. In the modified straight rise for overcoming friction analysis, we see that the von Mises stress decreased by 54.4%. The modified rise mounting system is still above the tensile strength of steel. However, our modified design still significantly decreased the stress, strain, and deformation in both statically loaded and overcoming friction cases. We also believe if we had exact dimensions from CURT, our design stress would be under this tensile strength.